Hello, we are Legacy Robotics, and we are proud to introduce our rover that is new for this year, FESC, for the University Rover Challenge 2026.
The rover's power systems are powered using two 24-volt and two 12-volt batteries to satisfy the rover's load and power availability requirements. The rover's computational electronics and sensors are powered by a custom PCB that acts as a voltage regulator and current monitor, which helps to create varying, stable, and noise-free voltage rails. From here, our embedded systems team utilizes CAN bus to design and maintain the rover's internal communication network. This allows for a seamless data transfer between all motors, onboard sensors, and computers. This specifically entails the rover's wheels, arm, and science payload. The communication system consists of a dual wireless link comprising the 900 MHz and 5 GHz frequency band to ensure the connection between the directional antennas at the base station and omnidirectional antennas on the rover. This entire system, from power to embedded to communications, works together to allow us to remotely command and control the rover.
Our arm's base joint uses a custom planetary gearbox with 4-stage gear reduction. This gives us continuous full rotation. The planetary gearbox provides high torque density and low backlash for precise motion during delicate tasks such as cable insertion, switch actuation, and autonomous typing. At the shoulder, we employ a 15-to-1 worm gearbox attached to our drive motor, delivering peak torque of around 93 Nm at the shoulder axis, while having nearly zero backlash. The torque capacity allows the arm to lift and carry the maximum SAR payload of 5 kilograms. Our elbow uses a 9.2-to-1 block and tackle cable drive system, which is coupled with the drive's motor internal reduction to produce around 45 Nm at the elbow joint. This system allows us to route cables compactly while keeping compliance low for accurate angular control. The wrist employs a secondary block and tackle drive with a 3.25-to-1 ratio to give fine control of pitch motion. In addition, a dedicated roll joint provides axial rotation of the end effector, allowing plug-in of the USB-C cable or inserting a test tube. For keyboard typing, we integrate a solenoid actuator on a rack and pinion linear rail. This rail allows the end effector to translate along a single axis while the wrist rotates, enabling us to type across the keyboard with only two motors moving at any time, saving energy. Our end effector is based on a 4-bar linkage gripper driven by a single motor. Motion is transmitted through geared links, so that moving one side automatically synchronizes the other. We use neoprene grip pads to enable securing lifting of objects up to 5 kilograms.
Our rover focuses on a rocker bogie type suspension, which works well traversing over difficult Mars-like terrain. We work with a 2-wheel steering system and an all 6-wheel drive, which works well with a differential bar attached on one point underneath the chassis, then 2 points on the side of the suspension arms, where it will maintain level stability for the chassis for the duration of the mission.
The science payload utilizes linear stepper actuators to lower the auger drill and drill the soil for cache collection. Using stepper encoders, we will determine when a soil depth of 10 centimeters has been reached, open the cache, determine when 5 grams of the soil has been deposited, and close the cache. As a science capability, an NPK sensor will be lowered into the drilled hole, displaying the soil's NPK content. Our main life detection system is the Bradford assay. A servo-powered scooper will collect soil and deposit it into a blender pre-filled with a buffer solution. Afterwards, peristaltic pumps will transfer the solution to cuvettes filled with Bradford reagent in the spectrophotometer carousel. After the reaction, the spectrophotometer will measure the reacted solution's absorbances at 595 nanometers, which we will use to calculate protein content in the soil from a calibrated BSA dilution curve.